Alternatively, we can also check the number of unique columns in matrix D as well. Look at the elements in column 2. The elements are 2, 2 and -4. So clearly we can see that the elements in column 2 have no relation with the elements in column 1. So C2 has no relation with C1. But look at the elements in column 3. 3, 2, -3. They can be obtained by simply adding the elements in column 1 and column 2. 1 plus 2 you get this 3, 0 plus 2 you get this 2, and 1 minus 4 you get -3. So notationally we write it as C3 equals C1 plus C2. So it means the elements in column 3 depend upon the elements in column 1 and column 2. So it means column 3 cannot be considered as a unique column. So total number of unique columns in matrix D is 2. Hence we say that rank of this matrix D is 2. Consider another example of finding rank of a matrix, and this time we are considering the identity matrix of order 3. The matrix having element 1 on the diagonals and element 0 on the off diagonals. So let's check the number of unique rows in this matrix I. Clearly, row number 2 cannot be obtained from row number 1, and row number 3 cannot be obtained from either row number 1 or row number 2. So it means all 3 rows are independent. So total number of unique rows in this matrix is 3. And similarly, we can see that the total number of unique columns is also 3, because all 3 rows and all 3 columns are independent. So we say that rank of this identity matrix I is 3. There is an important point to note in all the examples that we have discussed so far. And that important point is that the rows and columns always agree on the rank. The total number of unique rows is always equal to total number of unique columns. Isn't it amazing? Yeah, it is, and it's true as well. So in future, if you are supposed to calculate rank of a given matrix, there is no need to work out both cases. That is finding number of unique rows and finding number of unique columns. So you can only find the number of unique rows, that will be considered as a rank of the matrix, or you can only find the number of unique columns. There is no need to carry out both calculations, because ultimately the row rank, the number of unique rows, and the column rank, the number of unique columns, they are always equal. One last point before closing this lecture is what exactly rank of a matrix tells us. So rank tells if we have a chance to solve a system of equations or not. If rank equals the number of variables, then the system of equations has a unique solution. Let's illustrate this idea by considering a system of two equations. Equation 1 is 2x plus 3y equals 6, and equation 2 is 3x plus 3y equals 7. So we can write these two equations into matrix notation as just by writing the coefficients of x and y, 2 and 3 in the first equation and 3 and 3 in the second equation, and writing these x and y in the form of a vector, and putting equal sign 6 and 7, the values on the right hand side, in the form of a vector as well. And we can denote this matrix form as Ax equals B, where A is this matrix, X is this vector containing two elements x and y, and B is this vector containing two elements 6 and 7. So now look at this matrix A and check for the rank of this matrix A. The first row has two elements 2 and 3. The second row has two elements 3 and 3. And we can see that the second row has no relation with the first row. So it means there are two unique rows. So in this case, the rank of this matrix A is 2. So rank is 2 and number of variables is also 2. So if rank equals number of variables, then the system has a unique solution. We can say that these two equations will yield a unique solution for the values of x and y. So let's solve the system of these two equations simultaneously. The simplest idea is to subtract equation 1 from equation 2. So subtracting equation 1 from 2, we can see that 3y will get cancelled with 3y, and 3x minus 2x we get x, and 7 minus 6 is 1. So x will be equal to 1. So x equals 1, and then replacing x equal to 1 in equation 1. So 2 into 1 you get 2 plus 3y equals 6, or 3y equals to 6 minus 2, or 3y is equal to 4, or y equals to 4 by 3. So x equals 1 and y is equal to 4 by 3 is the solution of this system of two equations. So we can see that this solution is a unique solution. Only these values of x and y satisfy these two equations. This solution is unique because rank of this matrix A is 2 and the number of unknowns or number of variables in this system of two equations is also 2. So since rank equals number of variables, so the system has a unique solution. Let's consider another system of two equations. Now this time equation 1 is same as before, 2x plus 3y equals 6, but we have changed equation 2 to 4x plus 6y equals 12. So writing the system of these two equations in matrix form, we can write matrix of coefficients 2, 3, 4, 6 and then xy and then 6, 12 as before, and naming the matrix of coefficients as A, the vector containing variables x and y as x, and the vector containing these two constants 6 and 12 as b. Let's find the number of unique rows in matrix A. Row 1 has two elements 2, 3, row 2 has two elements 4, 6. So we can see that the elements in row 2 can be obtained by multiplying the elements in row 1. So 2 into 2 you get this 4, 2 into 3 you get this 6. So it means row 2 is not a unique row. So the only unique row in this matrix A is row number 1. So rank of this matrix A is 1. Since number of variables is 2, whereas the rank of matrix A is 1, so it means the solution of this system cannot be unique. Why? Because the rank of coefficient matrix must be equal to number of variables in the system. The number of variables in the system is 2, x and y. There are two variables. But the rank of this coefficient matrix is 1. So no unique solution exists. And we can see that there exist infinite solutions. Considering only the first equation, because second equation is just a multiple of first equation, so we can see that when x is 0, so then y is 2. So it means 0 and 2 is a solution of this equation. Similarly, when x is 1, so then 2 into 1, 2. So 2 plus 3y equals 6, or 3y equals 4, or y is equal to 4 by 3. So x equals 1 and y equals 4 by 3 is another solution. And when you replace x by 2 here, so 2 into 2, 4, plus 3y equals 6, or 3y equals to 2, or y is equal to 2 by 3. So x 2 and y 2 by 3 is another solution. And also when x is 3, so 3 into 2, 6, plus 3y equals 6, or 3y equal to 6 minus 6, or 3y equals 0, or y equals 0. So 3 and 0 is another solution. So we can see that infinite solutions exist for the system of these two equations, and these solutions are 0 and 2. We can replace x by 0 and y by 2. We can see that left hand side becomes equal to right hand side. Similarly, 1 and 4 by 3 is another solution, 2 and 2 by 3 is another solution, 3 and 0 is another solution, and so on. So there exist infinite solutions. So this concludes this lecture.